well-deserved and nice success of the renewal of the MCQST. Yeah, I just want to start with a little bit of publicity, because in Trento we have also a quantum center. So this is a beautiful view of the city of Trento, and we have around not only mountains and so on, but it's also actually a huge density of expertise in quantum science and technology. So we have the University of Trento with various departments that work on that. We have the Bruno Kessler Foundation and units of the CNR and INFN. We have also the ECT STAR. So this gives a very high density in a close, confined valley, so to say, really working on many different aspects of quantum science and technology. And so in 2018, we decided that it would make sense to join effort and found a joint center where we really work on all aspects of quantum science and technology. So from very fundamental to applied algorithms and on various platforms. What is also very important is technology transfer, where we are active. And a very important pillar of all of this is the education. So since various years, we already have a transdisciplinary PhD program in quantum science and technology. And we are working on establishing a master in quantum engineering, which for various administrative and so on reasons takes much longer than we were hoping, but we hope that at some point this will also come. Okay. If you ever come to Trento, don't only pass by to go to Bibione or to the beach, but stop by and visit us. Okay. Yeah, so I want to talk about holographic quantum matter and how to quantum simulate this. So this is a very exciting type of matter, field theory, that is related to gravity, also the quantum theories of gravity. It plays an important role in quantum chaos and quantum information in condensed matter, and now also for us in quantum simulation. And now, well, because there are all these interesting things there, I thought it made sense to actually structure my talk as follows. So first give you actually an introduction, what is this holographic matter at all? Where do these different things that I'm showing you, why do they all come together here? So I'm going to spend, I think, more than half of my time on the introduction, and then I want to show you how we can take a paradigm system for that, the Sachdev-Kitaev model, and actually try to implement this in a cavity QED setup. Yeah? But I'm also already happy if you take a little bit away what is holographic quantum matter. I'm already very happy. Okay, so where does this come from? We heard about people are trying to combine quantum physics with gravity, and we have a theory that is attempting to do this, which is string theory. And all of this comes from string theory. So the elementary objects of string theory are these branes that you may have heard about. So these are objects of a certain dimensionality that are embedded in a higher space. And it turns out that there's one specific string theory that where people have been working on, they found very interesting phenomena. So that's a theory of three-dimensional objects that are embedded in a 10-dimensional space. And now one can wonder about, okay, what are the low-lying excitations that describes this theory? It turns out if one has a very weak coupling between the strings, then this is actually described by some sort of strings that connect these branes, these elementary objects. If on the other side we go to very strong string coupling, well, the string coupling gives us how strong is gravity in the system. So if this is very strong, what will happen is that these branes collapse and they build something that is called a black brane, so it's a black hole essentially. And so now the low-lying excitations are, so to say, the dynamics of the matrix around close to the horizon. And so one can then, if one is a clever string theorist, one can write down what are the theories that describe this. So, by the way, this is a very naive point of view for someone who's not doing string theory. So what are the theories that describe this? So in this weak string interaction limit, this actually turns out to be supersymmetric Young-Mills. That's a non-abelian gauge theory at weak coupling. If you go to the other side, the dynamics is described by ADS5 gravity, so a classical gravity theory, again at weak coupling. And so this means that if we increase the coupling in some way, we go from a supersymmetric Young-Mills gauge theory to some sort of describing the low-lying excitations as a classical gravity theory. Now, Maldacena in the 90s came along and had this conjecture that actually this is not only something sort of smoothly connected, but we can also see it like this. If I take supersymmetric Young mills and I increase the coupling constant, well, I reach strongly coupled Young mills. And so the conjecture is that actually strongly coupled Young mills is nothing else, written in a slightly different way, than ADS5 gravity. Yeah, so the conjecture is that these are actually the same theory, just in a different language. And so what does it mean they are the same theory? One can try to formalize all of this. Well, being the same theory means they have the same partition function. If I have certain parameters that describe my theory, hi, on the quantum field theory side, and the same values of the parameters on the gravity sides, then the partition functions should agree. Now, what does the partition function mean? On the field theory side, we can write down a path integral where we have source terms, so the hi that describes the source terms for different operators, so these can be particle densities, currents, and so on, and these describe what's going on in the field theory. Now, what are the hi's on the gravity side? Well, on the gravity side, it turns out that the good way to describe this setting here is to fix the boundary conditions. Okay, so this is essentially a Dirichlet boundary problem, where we fix boundary values given by values hi of a gravity theory. And then it's a little bit complicated to show that it's actually a well-posed problem and so on, but then one can show that so here the boundary problem defines the entire the properties of the gravity fields in the bulk. And so from this, one can take, so to say, one step more and say, okay, well, this means I have, so to say, some field theory where the source terms can be seen as the terms that describe, that determine the gravity theory in a bulk. And so this is this idea, why this is called holographic. This is to say we have a field theory in a lower dimension which describes a gravity theory in a higher dimension, like what we have in a hologram, where we look at a three-dimensional image, but it's actually encoded in a lower dimensional, in a two-dimensional photographic plate, but we have all the information about the image in this lower dimensional system. Okay, so in the same way we can say, well, this field theory has all the information about a higher dimensional gravity theory. Now, we can wonder why, how can this work actually? The bulk should have many more degrees of freedom. Also, so if you think about a circle, if you look at the surface of the circle, it scales with r, but the area scales with r squared, so it's much larger. No? But here, because we have an anti-de Sitter space, we should see it, so we can try to put it in on a flat space. Then this curved space would look like this. So each tile here has the same size, so to say. And we see that towards the boundary, we get more and more and more and more tiles. So it becomes more and more dense, which means that if one takes an integral here, if we take an integral close to the surface, it scales in the same, so a line integral, so the surface, it scales in the same way as integrating the entire volume from the center to the boundary, which is completely counterintuitive, this you're not used to, which means that in some sense, the surface is as big as the entire bulk. And so it means it can contain all the information that is relevant. And now this field theory, this is the holographic quantum matter. And now the interesting part is that, so, well, I said it's a classical gravity theory here, but actually if you take some deformations from this field theory, so finite size systems or so, then this translates actually to quantum effects in the gravity. So one can try to learn about quantum effects in complicated gravity theories by studying the field theory at the boundary. And this is why people from quantum gravity are excited about this connection. And now, since if one has this connection, there are also immediate physical consequences that one can go from one side to the other. For example, if one has a generic excitation of a black hole, the black hole, I guess one do black hole thermodynamics, and one sees that these dissipate away with a time scale which is given by essentially the only scale that matters, which is the temperature of the black hole, so the inverse temperature. Okay? And this means that now a perturbation on the black hole side should also translate to a perturbation on the quantum field theory side that dissipates away in the same fast manner. Yeah? And so there's another very influential paper where also Maldacena was in it with Schenker and Stanford, where they conjecture based on some physical assumptions that the chaos measured by out-of-time ordered correlators can develop no faster than exponentially with a Lyapunov exponent that is given by the temperature, essentially. Okay? So they say there's no system, essentially, that can be where the information about the perturbation can be dissipated away faster than this scale here, so the inverse of this time scale. No? Which gives us this second, why is quantum information interested in this? Well, because these are like the most chaotic systems that there are. So that's conjectured, and we don't know of any system that would be faster like that, so it seems reasonable that this is indeed true. So these are the most chaotic systems that exist. Now, we can wonder, okay, so we want to find a field theory that saturates this bound that is as chaotic as that. So which field theories are these? One can look at the systems that one has around. And so if you have a system that has quasi-particle excitations with a certain mass gap, one finds that actually this time for things to dissipate away, well, this is given by the lifetime of the quasi-particles, so they need to scatter into each other, and then they lose information. So, the mass gap enters as a scale, and so one can show that it actually goes exponentially with m over the temperature. You can say, okay, maybe it's faster if I have a gapless system because I don't have this scale anymore. So if you take a Fermi liquid theory, for example, then one sees that the time scale for things to dissipate away is 1 over the temperature squared. And so this leads us to believe that systems that can saturate these bounds must be systems that don't have any good quasi-particle excitations, because all of these are much larger. Now the temperature goes to 0, 1 over t square is much larger than 1 over temperature. So these times are much, much larger. So the fastest chaotic things that can be, we believe that they have to be systems that don't have quasi-particles. And so this is where the condensed matter physicists become excited about this, because these non-Fermi liquids, they are still relatively poorly understood. And one believes that they describe phases like these strange metals and so on that appear in high-temperature superconductors. Okay, so we can also hope to, by looking at these quantum systems, to learn something about the phenomenology of high-temperature superconductivity. Okay, so what are these? This is now all on the phenomenological level. Let's get a bit more concrete. What are these field theories? How can you think about them? I mentioned in the beginning this supersymmetric Young-Mills, and if you write down the Lagrangian, it looks like this. So not as complicated as the thing you've seen in the previous talk, but it still becomes a very, very long expression. And there are many different fields in there, actually. And the relevant, so there's a gauge boson there with a gauge theory, and the relevant theory is if you have a UN group and the n goes to infinity, then we recover the type 2b superstring theory in ADS5. There's actually also a 5-sphere in there to match the dimensions. Okay, this is very complicated, but actually it has been very successful, because by looking at this gravity theory, for example, one has learned a lot about strongly coupled gauge theories. And so we would like to learn about SU3 in 4 space dimensions. Now we have Young-Mills I'm confused about the dimension. No, it's fine. Yeah, the 4 space-time dimensions. So we have Young-Mills. So we would like to learn more about SU3, but one can try to understand what is possible in principle in non-abelian gauge theories. And this has been very successful, actually, to describe also things happening in heavy ion collisions. But okay, let's see if there are simpler models. There's actually, for a long time known, this Banks, Fischler, Schenker, Susskind matrix model. So this is 9 n times n Hermitian matrices, and then there are 16 other matrices that are matrix valued spinors. And we have also a constraint here on all physically allowed states. So this is still a very complicated model, and we need to send the matrix dimension n to infinity, and then it becomes type 2a supergravity. So still very complicated theories. And actually about this model here, from this side, we don't really even know how the ground state looks like exactly. So, yeah. Okay, so this sounds like very complicated, and so how do we put this into practice? Well, there was a breakthrough in 2015 when Kitaev, in this famous talk at KITP, proposed a model as a simple model of holographic matter, which now is known as the Sachdev-Kitaev model, because one realized very early that it's actually very similar to a model proposed by Sachdev and Ye in the context of condensed matter systems, non-Fermi liquids, and so on. So also as the Sachdev-Kitaev model. And this model, it looks like this, so it's much more compact. Okay? So we have here only interacting fermions, so n different modes, essentially the fermions that scatter into each other and go into other modes. Yeah? So this can be complex fermions or Majoranas. Hoffman writes this in Majoranas with complex. This means this corresponds to a charged black hole. Okay? So one can take both versions. Now the special thing about this, we want this to be an as chaotic model as possible. There should be no quasi-particles emerging and so on. And to achieve this, well, first of all, the interactions, they are assumed to be all-to-all, so really all modes can scatter into all other modes. And also this, every interaction index here, JIJKL, is taken completely randomly from independent Gaussian distributions. Well, you'll see that it's much simpler than the previous models that I've shown you, but it's still very complicated. We have all-to-all interactions, very long-ranged, and there should be no correlations between the interaction indices. So if I change one of these indices here, the interaction should be completely different, randomly different from others. And then, well, okay, so then if you take n to infinity, then this becomes equal to another gravity theory, Jackiev-Teitelbaum gravity. So it's a much simpler gravity theory, but still, okay, we have to start somewhere. Yeah? And so this is really a prototype for holographic quantum method, so it fits the bill of all these things. I mentioned it's dual to Jackiev-Teitelbaum gravity. Actually, this out-of-time ordered correlator decays as fast as possible, so this is extremely chaotic, and it has no quasi-particles. So people look at this as a phenomenological model for strange metals. Okay? And so now the question is, okay, so we want to do this model, but it's also so this characteristics that we have infinite-ranged, random, and uncorrelated interactions. The question is, how do we get this out in a physical system? Yeah? So we're not the first ones to think about this. There have been various proposals in graphene flakes, optical lattices, and so on. These are very, very important and influential proposals. But they're also very, very hard experiments. On the other side, people have thought about how to take the model and encode it in a quantum computer. There have been various works, but there, essentially, we have n smaller equals 7 modes at the moment. So it also doesn't look extremely scalable at the moment. Yeah, so this is why we thought, okay, so maybe we can find another platform where we can implement that model. And so we believe, so this is the second part of the talk, essentially. So we believe that an ideal platform is cavity QED, and this is a work that we are doing together with the groups of Jean-Philippe Trento at EPFL and Julian Sonner at Geneva. And so the idea is, okay, we put a cloud of atoms into a cavity, and then we get out an effective SYK interaction. Okay? Okay, so I just want to give you the main ideas of how this works. Okay, so essentially, so the idea is, okay, so we have a cloud of atoms that are in 2 states, a ground state and an excited state, and they are in an optical cavity, so they couple to the cavity photon. Which means that the states to describe the systems is the internal atomic state and the number of photons, so we can write down the spectrum, we have some energy of this atomic transition, so from ground to excited, and then we can also put in the cavity photon, okay? Which is a little bit detuned from the atomic transition. Now, the atom and the photon can exchange excitations, and so we can write down the Hamiltonian for this. So a ground state atom can become an excited state atom if it absorbs a photon and vice versa. Okay, and then this can be an off-resonant process where we have a detuning here. Okay, so let's look at this. Well, so if the cavity photon, it touches all the entire atomic cloud, so it's actually something that talks to all the atoms. So it's somehow long range, which is what we want. But how this looks like, this depends on the mode function of the photon, and these are Hermite-Gauss modes, for example, and so they are not at all random. They have lots of structure in there. So we want the random interactions. So how do we achieve this? The first thing that we do is we assume that we have a multimode cavity. So one can also do it with a single mode in a trotterized fashion, which we've worked out in this work. But let's just for now think about a multimode cavity. And now the atom can exchange excitations with all these different modes. So it can go to the excited state by absorbing one of these photons. Now to increase the energy scales, we put in also, we proposed to put in, this is not yet done, this experiment, but okay, we are hopeful that Jean-Philippe will do it at some point. So we had proposed to put in also a classical drive, which off-resonantly addresses the transition from ground state to excited state. And we measure all the energies with respect to the detuning of this classical drive. Okay, so we have this detuning of the cavity modes, and now we can do off-resonant Rabi oscillations also here, so we can go from the ground state to the excited state thanks to the drive, and there's a detuning here of the excited state. Now what we do is we assume that these detunings are the largest energy scales, and we do 2 layers essentially of perturbation theory to get an effective theory for the ground state atoms. So we could go through all the calculations they are found in the, but they also repeated here, but also in the previous paper from 2023. These are all detailed, but one way that I think is nice to think about this is just diagrammatically. Okay, so what does this process here mean? Well, an excited state atom comes in and it emits a photon, and in this way goes back to the ground state. What does this process mean? Well, for example, a ground state atom absorbs something from the classical drive and is promoted to the excited state. So these are all elementary processes. And now, if the detunings here are the large energy scales, we can look at what is the resonant process if we start in the ground state. Well, the ground state atom, thanks to the drive, goes virtually into an excited state. It goes back to the ground state by emitting a photon. The photon is captured by a different ground state atom, which is now an excited state, and interacting with the drive goes back to the ground state. Okay, so essentially, if we think of what is this effective process doing, well, it takes 2 ground state atoms in and 2 come out. Okay, so you have 2-2 scattering. And because there are these cavity modes there, this is long-ranged and all-to-all. Still, this is not random, so we need to put in one more ingredient, and this is a speckle pattern, which does the following. So it goes from the excited state to an auxiliary level and generates an AC Stark shift. And now, since this is a spatially random speckle pattern, it means this translates into a spatially random AC Stark shift. And now if we do the perturbation theory, so here is the formula that actually comes out. We see that ground state goes back to ground state. And now we have here, in the effective interaction strength, we have these random detunings. Okay, and so now one can express this in the good basis, which is the single mode basis, but we've actually checked that this is independent of the different bases. We go through this, and then we get this two scattering. And there's also actually a single body term that one needs to compensate, because the SYK model has only the interaction term, but one can do it, so we have to discuss in the paper also how to do it. And so essentially, we get out a random interaction, and we can compute what it is by computing the overlap integrals of all the different modes and so on. Okay, now of course one can ask, well, okay, there's something random going on, but this is actually good enough. And so we wanted to convince ourselves that this actually works. So we really did a microscopic calculation. So we simulated a speckle pattern and then took all the different modes here and computed all these overlap integrals to see if these interactions are really random in the way that we want. And so this is the distribution of these interactions, and we see indeed they are randomly distributed. But I said before that for the SYK model we expect a Gaussian distribution. This is if you open a random paper about SYK model, it says we assume a Gaussian distribution. Well, the Gaussian is this one here, and we see there's quite some discrepancy. Actually, we find a Cauchy distribution. And this cost us something like 3 months or so. We were trying to tune all the parameters, looked at system size, scaling. So there has to come a Gaussian out. Why don't we get a Gaussian? And it was just not coming. And so we got a little bit depressed. So we went back to the previous papers, looked at how did they do it. And a couple of those papers, they just say, okay, we have something random, and then the law of large numbers tells us it will be a Gaussian at some point. Okay, so this is an easy way out, but we wanted to make it a bit more precise. So we looked at other papers, and some of them also did such microscopic calculations as us, and these were so nice to give us their data. And so in the paper they just say, okay, it's now Gaussian distributed, roughly Gaussian distributed, we are happy enough. But if you look closely, you also see that there are deviations from a Gaussian in certain parameter regimes. So for example, here it's also much more a Cauchy distribution than a Gaussian. Here, this is now a complex number, so it looks a bit different, but the Gaussian fit would be this, the Cauchy fit is much nicer. Okay? So this appears to be something that is relatively general, and we now also understand that this comes because there's still some correlations between these interactions that are there. Okay? Why am I insisting so much on this? Well, because I think this generates a very interesting interplay between theory and experiment, because thinking really about the implementation, how is it done in practice, we see that, well, the Gaussian is an oversimplified assumption. And now the natural theory question comes. How much can we deform these distributions and still get the same physics out? What is allowed? I mean, people know that the Gaussian is mostly also for commodity, but how much can we actually go and still get the system to be so chaotic and holographic and all these things? Okay? So this also, I find it very stimulating also now as a theorist to think about this. Okay, then we did other tests to see, so by the way, we tested the Cauchy distribution works, so it gives the same physics. We also simulated the system, now we took the interactions and then simulate the time evolution of the full system. And for example, we looked at out-of-time ordered correlators as a function of time. How do these evolve? Well, this SYK model is the most chaotic there is, so it should be very, very fast. And now we see that if we change the number of modes in this system, it becomes more and more random, and we actually go closer and closer to the dynamics of the SYK model. So can we really recover this in a controlled way? And it can actually be a nice thing to see if we talk to few modes, we get something that is much slower, much less chaotic, and so on. It's more like even becomes at some point a spin glass type behavior. If we increase the number of modes, we get all of this frustration in there and it becomes very chaotic, and we go really to the SYK model. Yeah? And well, it is also interesting that the timescales here are very fast, so if we knew how to measure the OTOC, then this could be something that is as accessible on the timescales that are available. We also did other tests, for example, for the experts, we looked at the spectral form factor, which we also see if we change the number of modes, we go to that of the SYK model, and there's some interesting things about chaos that one could say here, but essentially we recover the right physics. Yeah? Okay, I think I need to conclude. So what I wanted to show you here is that this cavity QED setup is really an ideal platform for pursuing this SYK type, holographic quantum matter type of physics. But then in the beginning I showed you, well, it's interesting for condensed matter, for quantum gravity, for quantum information and quantum chaos. Why should it be interesting for someone doing quantum simulation? I think there are also many reasons for that. Well, the first one is that we're thinking about this very complicated theory, but on the way there are actually simpler theories which are still very, very interesting. For example, if you look at these interaction diagrams, if we can, for example, get the disordered central mode model if we look at the simple theory, or if we hook them up in a simpler way, just doing one order of perturbation theory, we get, for example, a disordered LMG model. And so this has been implemented by Jean-Philippe and his team. And so the interesting physics also that one sees there's gray polaritons, Anderson localization, and so on, which one can investigate here. But then there's also another thing that I think this stimulates very interesting research questions. Yeah? So, for example, so for us it's important to think about now what can we actually observe. So can we observe spectral form factors and OTOCs in the system, or are there other observable features of this extreme chaos? And by thinking about this, we discovered that in the SYK model there's actually a universal dynamic. So if we do a quench, First of all, we see that the system loses any information about the initial state in a super exponential way. Okay, but then we also discovered the initial state, if a local observable, they had some initial value, but if I now just scale this out, so just divide by the initial value, we saw that all these curves collapse onto each other. And this is an expression of the SYK model being essentially as chaotic as you can get. So it essentially becomes a sort of a random matrix theory in an almost pure form, but implemented in a many-body system. Yeah? And this is what this shows. Okay, so it's also interesting, let's say, new findings that come. We can also, I talked about these imperfections. Now it can go back to the gravity side, and we can ask, okay, we have now different types of imperfections. What did they mean to the gravity theory? Do they mean something interesting? Can we analyze how they changed the theory? Of course, these systems are dissipative, so we can wonder, there's all this new field, essentially, of dissipative quantum chaos, which is now receiving lots of attention. And one last thing that I want to say is, well, we're thinking here about quantum simulation. Okay? So when we do quantum simulation, we want to do systems that are as hard as possible for everyone else. Okay? We want to have something that you cannot compute on a classical computer. And so we wanted to understand what is actually the complexity of these systems. Now, one way to study this let's say, in a many-body setting is to look at how strong is the entanglement in the system and how strong are things like the non-stabilizerness magic, if you've heard about these things. Okay? So different markers for different types of complexity that a system can have. And so in this recent paper, for example, we take a model that tunes between SYK and the Ising model, and we find that the SYK region is really saturates all these different markers, and then if you go away, they drop rapidly. Okay? So there's now a new conjecture that I'm doing is that I think that this holographic quantum matter is the most complex type of matter that there is, and this is why I think it's also one of the most interesting targets to try to do in a quantum simulator. Yeah, because everyone else will have a very hard time to try to simulate this dynamics. Once you go beyond 24 modes or so, then it's done. Yeah? Okay, with this, I want to thank the team that have been working on this. So it's Zsombor Bandyobatay, Andrea Legaramandi, Alex and David on the implementation side, and for this last thing about complexity, were also Gopal and Alberto involved. And with this, I thank also you.
Thank you very much for the talk. Unfortunately, the entire time allotted for the talk has passed, so I would suggest that we shift all questions for the lunch break. Before you leave for the lunch break, please, there's an announcement from the organizers.
Yeah, thank you, Andreas. So just a quick reminder, so we are voting for the Best Poster Award. Please put in your favorite posters into the app.